review recent progress in quantum error mitigation. So Kristan can start. Yeah, and if you have some questions, please put them on Slack. Thank you.
Okay, thanks a lot, Libor. Thank you very much, everyone, for the invitation. So as Libor said, what I'm going to be talking about is a review and some recent result that we have obtained. So let me go and talk about the outline. So I'm going to spend quite some time on just recapturing like the old error mitigation protocols, which are now by, I don't know, probably 4 years old by now. And so there's been a lot of development in the meantime. But maybe what I'm trying to do is maybe explain a bit what our motivation was back then and why we did certain things that way or didn't try other things and so forth. So maybe that's why that's helpful and it's going to build on. That's what I'm going to be building on. The other thing is I'm going to talk about briefly talk about two new recent results. And one result is that deals with readout errors and how to potentially mitigate them, and a neat little trick to do that. And then I'm going to talk about work that is to be published within a few days, which that is trying to basically bridge the gap from a non-fault tolerant to a fault tolerant device. And the question is there some meaningful place to play with error mitigation tricks there in trying to bridge such a gap? So that's what I'm going to be talking about. So I guess everybody's familiar here, but so just a very brief setup. We're considering, for starters, noisy, small, mid-scale to large devices that are available sort of in the neat term. So choose your favorite number of noisy qubits. And the general approach that has emerged through various proposals is always sort of fits into that framework of saying, well, we know there is decoherence, we know things get bad. And so after a while, we should just stop computing once things get bad. And what we should do is we should restrict ourselves to sort of shallow depth circuits that are sort of within reach of decoherence. And the only thing we care about is not, let's say in this case, it's not even proper sampling statistics, nothing fancy, just we want to estimate some expectation value in the end. Okay, so what's the tricky bit about that entire picture? It's basically, it assumes that, well, if you go up until to decoherence, everything is just fine. And once you go past your decoherence times set by, say, T1, T2, things start to get sort of tricky and become really bad. And it looks kind of in the head might look like this cartoon where everything is just initially hunky-dory and then everything really turns bad pretty quickly. Okay, and but that's not actually what happens. The answer is that it actually becomes pretty bad from the beginning. And you just have you immediately start decaying, everything decays sort of exponentially. And so your 1 over your decoherence times is just your 1 over E time, basically, once you've decayed that far. So you might actually be pretty far off from where you want to be already, although you restricted yourself to a shallow circuit. And the entire crux is basically to just go and accept that and say, well, in error mitigation, we're not going to be able to fix that directly. We're not going to change the fact that the device is that decohering. We're not going to be able to extend the reach. We're not going to be able to compute anything fancy. But at least let's try to make that naive picture that we initially had be more viable with some method and classical post-processing without generating too much actual overhead on the device. And so does that actually matter? And the answer is yes. So a couple of years ago, 4 years ago now, we ran experiments on what is by now considered probably a very small device. And what you see immediately, even that for those small devices that where you compute energy contours, you realize that yes, decoherence is the dominant error, and it becomes really painful to deal with that. So, and it's sort of very predictably so because the simulations do that as well. So much for our motivation to say, well, okay, let's try to fix stuff in the window. So allow me to basically now do a brief recap of basically the two protocols. And so let's start. The two protocols are basically what I'm going to talk about is a small overview of zero noise extrapolation that I think people have mentioned earlier before, but I can basically tell you what was important to us back then and how our perspective has changed in the meantime. And the other protocol, which all the subsequent ones I'm going to be talking about builds on is the probabilistic error cancellation method, which I'm going to be talking about. So the zero noise extrapolation was proposed in 2017 independently by us and Ying Li and Simon Benjamin. What is the basic idea? So from our setting is you assume a very simple model. You assume your system evolves dynamically as it does. Your circuit can be described by a time-dependent Hamiltonian. And what you would then realize is that the actual dynamics is modeled time-dependent Hamiltonian plus some noise term. So that noise term can be pretty much anything. It doesn't have to be Lindbladian. It can be coupling to the environment. The only thing that we shall require is that it's constant in time, and that parameter lambda in there doesn't really mean anything physically. It's just sort of like a dummy parameter. And the basic idea of all those schemes is now basically, of the zero noise extrapolation scheme, is basically, oh, if you in the end measure some expectation value, you would like to treat that expectation value as a function of that dummy parameter lambda and see what you can do with this. So what's the basic idea? If you treat it as this function and you assume that you have a knob that allows you to turn those parameter lambdas, then what you could do is you could turn that knob, measure the same expectation value at different noise strengths, stretching or changing the value of lambda. Once you have that changed, there's a simple system of linear equations that you can solve, an n by n system. And then what you do is you recombine linearly set expectation values to produce an estimator. And the nice thing is that this estimator has a guaranteed bound to be closer to the true value when you do that. So this is, from our perspective, this was actually a very important point, that we are able to basically analyze what that protocol is doing on a formal level, right? So there's a lot of stuff that is basically disappears in that delta star, which is sort of your largest experimental error. That basically means, well, how wrong are you in evaluating your energy values at different points and so forth. But what's important to us is basically to see whether, oh, there's some way we can understand why that protocol would work and what it is that makes it work and what the limitations are. Because if you then look at the error scaling and plug in certain models, then you realize that, oh yes, there's actually a limit on how far you can play this game, and you shouldn't go beyond said threshold that we talked about earlier. Okay, and so simple reason why does that work? Well, the entire magic behind that approach is basically the Richardson extrapolation protocol, which is something that was invented now over a century ago. It allows you to basically cancel term by term in your error expansion of that function in lambda. So that was the basic idea there. Okay, so coming to sort of the experimentally most painful point is, so how do you go and measure these different values of lambda, which enter expectation values, different values of lambda? So the idea we thought about then is, wait, we really want to go, there's a trick. If you assume that the coupling is stationary in time, then you can start rescaling your dynamics. And once you are able to rescale the dynamics and don't touch the noise because you don't have any control over that, in a rescaled frame, this amounts to just multiplying that noise strength by a fixed factor if all the assumptions are met. And that's kind of important that all those assumptions are met. And so based on that, the only thing the experimentalists, in quote unquote, only thing the experimentalists have to do is actually stretch out the genuine evolution that happens on the chip in the assumption, in the presence of constant error noise. And so if you do that, then yes, the expectation values of many things do get better, as can be seen in experiment, even for these small systems. So, but there are a lot of experimental considerations that go into this and make that work, because all that magic basically disappeared in that factor delta star, right? So there's sampling errors, there's readout errors, there's your wrong stretching and calibration of the gates. You know that the model isn't actually constant in time because there are T1, T2 time fluctuations. And a lot of the experimental work goes actually into dealing with exactly that you basically stagger your experiment in a particular way so that you can basically fluctuate with your T1, T2, that you tune up your gates so that you really have that stretched evolution as opposed to just tuning up your pulses, because that's going to lead to something that's horribly wrong, and so forth. So that's the basic idea, but it's still very painful. So one thing is that has been proposed in the meantime is actually something that is a lot more friendly on people, that if you wanted to have sort of limited access to the device, or if you wanted to not dig too much into the experimental details and actually getting that to work. And the suggestion was basically, well, suppose you have noisy gates and you have a very dominant noisy gate, which is proposed in this method. What you could do, which is a lot easier to implement, is basically you go and you take that noisy gate, and if you know that it's independent, so if you square to identity, then you could insert some identities by squaring that, and basically you power the noise that way. What I would like to point out that can work. However, one has to be really, really careful about the noise, because you have to make very strong assumptions about noise. So as a simple example, so if you just look at a very, very simple noise model, you say you look at just standard Pauli noise, which has the nice property that Pauli vectors or Pauli matrices happen to be eigenvectors of that noise. You can really see what's going on. Then basically, oh yeah, they depreciate by some fidelity. And now if you raise said noise 3 times, because the semi-group depreciates 3 times stronger. And indeed, yes, your fidelity would get worse. However, if you look at that noise model, what you actually have to do is you have to do C0 poly noise to the 3rd power. And if you calculate, because you can do that easily by hand, you realize that, oh, it's not f to the 3rd power of what you're doing, but you're starting to mix in different poly noise team, and they can be quite differently. So it may happen that if you have noise that is not completely uniform across the fidelities, that it's very difficult for you to know where you end up with the stretching, and you extrapolate from a completely wrong point. So that's something we have to be careful to make sure that the noise is basically in such a nice way that that the C0 gate just amplifies the power. Which, if you have some structured noise, which you start to see in more, if the devices get actually better, becomes actually kind of tricky. So that as a small cautionary comment. So continuing with that, let's talk about the second method that we're thinking about. So the probabilistic error cancellation method, I don't know, I suppose, depending as a review. So you can, the simplest way to basically understand that is, suppose you're in a very favorable and nice setting where you know that there's only 1 error at the 2nd qubit. And that is just very nice depolarizing noise and just happens after the 2nd gate that you apply on the 2nd qubit. And you could try something that a priori sounds a bit naive, which is basically to do the following. You could just try to apply the inverse matrix of that noise. Okay, the crux here is that this is, of course, not a channel itself, so it's not a physical operation that you can write as a channel, but what you can do is you can write it as a linear combination of channels, renormalize the channel, add signs where they're positive and negative, and have sort of like a quasi-probability representation of what that gate should be doing. Because what you can do now is you can sample these individual physical channels that constitute that decomposition with their probabilities and assign signs accordingly to that thing. And this is something you can actually implement by sampling over random circuits. And what you realize is you produce the correct expectation value, you remove the bias up to a multiplicative factor. And that's sort of the painful factor. Now, talking about that is, of course, a very naive noise model. But to see that this should work in general, you could think about it that way. Suppose you would like to implement a unitary circuit with all gates that are ideal, but you only have access to a basis of noisy operations, meaning some poor experimentalist has to go in there, measure out all those noisy operations, and then basically go and do very excellent, very precise tomography on those things. But if you have enough of those elementary gates, you could play the same thing and say, well, the clean unitary that I would like to implement can be written as a linear combination of those noisy operations. And then once you're actually able to do that, so the clean unitary as a CP map can be written as such, what you can play the same game as we did before, where you say, well, you can promote this to a quasi-probability distribution by renormalizing and adding signs in front of for every circuit that you compute. Okay, so what's the crux here is basically if you rewrite your actual expansion in terms of a probability distribution and add the signs, you're incurring some overhead with this damping damping factor. Okay, I think it goes the wrong way. Never mind. Okay, so what is that you do is you produce a given statistic, right? And that statistic is bias free but has a massive variance, as we'll see shortly. So what happens? So what happens is basically you evaluate the expectation value of that statistic, and ideally in infinite shot limit, this is the quantity you produce, is the correct expectation value noise free times a given damping factor. In practice, you have to draw a finite number of samples, and so what you have is the statistic that you produce in the end is close to the expectation value with high probability plus some sampling error. In order to fix everything, though, what you have to do is you have to divide everything by that damping factor that you learned from doing the noise tomography. And that means if you want to achieve a particular precision delta, you have to pay the price in a polynomial of that damping factor. So you have to damping factor squared many times more samples. And what you realize is basically that if you look at this for some simple noise model, say even the depolarizing noise, you realize that this grows exponentially. So this damping factor basically grows like you would expect, because you're having a sign problem effectively, and you're trying to renormalize what you do with the sign problem. But it's sort of kind of a weak sign problem, right? Because the basis is only 1 plus c epsilon. So if you choose roughly L of the order of c epsilon, it behaves as a constant, right? And so that sort of sets the limit of how far you can go there. Okay. So those were those basic methods that I wanted to recap. And now let me dive in and talk a little bit. Whoa, I'm way too fast. Dive in and talk a little bit about some recent work that we've been working on. Okay. So there's in general. So one of the other painful ideas that you can have, one of the painful problems you might be working with is basically that you have readout errors, right? And those readout errors, they depreciate what you're measuring and so forth. And they're sort of modeled by a classical noisy channel. And so what you could do is, like people have done for a long time, what we've been doing for a long time is really to do the brutal thing. If you have a low number of qubits, that you just basically go and measure out what that stochastic channel does. And then you just brutally invert that stochastic channel, apply that to your expectation values. Okay, and that works apparently in practice. So with caveats for these expectation values, you can look at that, and they do get better. But then in the meantime, people have basically come up with a lot of other and nicer schemes, basically, or more advanced schemes, where there's neural networks that are able to predict the correct outcome after they've learned it. There's certain model that we could, and so but the neat thing is there's actually a really simple observation that you can make that makes things actually really tenable and easy to deal with these readout errors. And so what I'd like to present is sort of an idea that of a recent paper that we published with Evud, Zlatko, and myself. And so to point out, Evud has been actually the one that proposed doing that in the first place. So one should definitely give him the most credit for that. And I should also point out that briefly before we published that, there was a related work by Chen Zheng and Stephen Flamia. And what they've done is you could treat, or what they do is basically the more general version of what we've done. So they, as I'll talk in a bit, they'll twirl about the full Clifford group and so forth, and then divide out and so forth. But we only twirl about the local noise. Okay. So what's the basic idea? It's really simple. So what you want to do is the following. So you want to just basically have a simple way of fixing expectation values. And what we try to do is to be sort of we try to not write down a specific model of the noise. That's why we call it model free. And so what is the idea? So you could imagine there's a twirling operation, just like with Clifford's, but in the case of the readout, what you could do is you just apply random X gates. And you basically go on the other is saying, you realize, okay, let's try to apply those random X gates. What you can do is you can try to fix the X gate by your new assignment of bits on the parity functions, i.e. on the functions that are Pauli Z observables that you want to estimate. Okay, so what you can do is basically, it's sort of like noise twirling, but on the measurement readout. And so the way you would go now is basically you would start and just noise twirl your standard A matrix without running any circuit. You just noise twirl the stochastic matrix, and what happens then is that after twirling, this matrix becomes diagonal in the Pauli in the parity basis. So it's not the Pauli's because it's classical strings in the parity basis, right? And so it's just noise. That means that noise appears from readout only as a multiplicative factor in front of all the Pauli Z observables that you shall measure in the end. So maybe I should point out, you only have to worry about Pauli Z observables because what you would do in practice is anyhow you rotate into the Z basis before you measure. Okay, and so what you would do then is basically, if you look at actually the entire error mitigation protocol is, you first go, you estimate that multiplicative factor by Pauli X twirls, and then after you've done that, you basically go and you run the same twirl on the readout, but now you run it together with a circuit, right? And so that you know now basically your expectation value is being depreciated by a multiplicative factor. And what you can do is you can divide said factor out. So that's basically the procedure. The first thing is you calibrate, you measure out that multiplicative factor, you divide out by that factor in the end, and that basically is supposed to give you a better error. So the nice thing is it's really simple to implement because you just do bit flips in the end and then do classical post-processing. The other thing is, it sort of doesn't depend on a noise model. You can just do it right away. Okay, now you can actually derive bounds for that, and what you realize is, so there's a standard measure concentration bound that you can consider. What is sort of important to consider here is that when you start dividing out, you're dividing out by a quantity that you, just as the earlier case, have estimated. So there's some additive error, additive sampling error with that, and that depreciation factor can basically decay and be smaller than 1, and it is smaller than 1. Now that means that, just as was the case before, that leads, if you divide that out, it leads again to a blow up in variance, and so that means you have to take more shots in order to estimate that, but you have a sort of controlled way of understanding by how much that grows. So, but if you look at those models, and of course that factor depends on the noise, because it's sort of like the eigenvalue of the X-twirled Pauli noise, you realize that that thing actually also grows weakly exponential, where the base is again determined by the strength of your measurement readout error. Okay, so that was the point number 2. What I want to transition to now is actually another project that we've been working on recently, and that isn't published yet, but shall come out soon. And so the question that motivated us is the following. So right now, we thought a lot about error mitigation. The goal is here that you have a hardware-friendly technique that is supposed to be fighting noise. It has, of course, problems, as we did, because it's limited by scaling. You're only set within that window where you're efficient, and otherwise it starts scaling exponentially. And then you could wonder, okay, in that setting, are there any quantum algorithms that are useful, right? On the other hand of the spectrum, we all know this is where we want to go to. You have a fault-tolerant quantum computer that uses actual quantum error correction, and there's a large physical and experimental overhead associated with that, as people know, and has very stringent hardware requirements and so forth. But the cool thing is, you have genuine quantum speedups with provable runtime. So the question is there some regime in between, going from error mitigation and noisy devices, where you can make progress basically on developing hardware and developing codes, where you can already reap some midterm early benefits before you actually go to the fault-tolerant setting, and could you use some kind of error mitigation technique to do that, right? So the goal here is, you transition, so you may have to make assumption that you're at a different stage and you have some error correction capabilities. And what we're looking for is sort of like a relevant way where you could insert error mitigation. Okay, so that's sort of like the challenge that we've been looking at. And so what we basically have been working on is joint work with Christophe Piveteau, David Sutter, Sergey Bravi, Jay, and myself, and should appear soon in the archive. And the idea is to basically see what is like the practically most painful component if you're actually trying to do error correction in mid to near term. And the idea is then, well, maybe you can actually use error mitigation techniques to deal with noisy T-gates, right? And so this is, what I should point out particularly is that most of the heavy lifting of that work was done by Christophe, who is now a graduate student at ETH in Zurich, and by David Sutter, who's at IBM in Zurich. Okay, so if you think about this, if you want to insert yourself, or if you want to insert error mitigation in some way, step between full actual quantum error correction, you basically have to wonder, okay, what are actual challenges in fault-tolerant quantum computing? And everyone knows that, well, that let's assume for now that if you want to implement an error correcting code, you of course want to apply a set of transversal gates, which means these are gates that can be implemented basically with only very shallow circuit and a shallow depth. And the reason why you want that is essentially that you can then show that after subsequent rounds of error correction, your errors haven't spread too far, and you actually have a chance of correcting them. So you act between various code blocks and are allowed to implement transversal gates. However, the big problem is, of course, as people probably know, is that it's not possible for a quantum error correcting code to actually implement a universal set of gates that are all transversal. That's the famous Easton-Nil theorem. And so what people do there to go around that is, for instance, what you could do is you could do transversal T-gates non-transversal T-gates by a procedure called magic state injection and magic state distillation, which would I think, yeah, which Sergey and Kitaev invented quite a while back, right? And so that allows you that additional research of basically injecting noisy T-gates, distilling them, and then building a T-gate gadget that implements them, allows you to become universal. Okay, so what's the overall idea, which is rather simple. So we realize, okay, the T-gates, they might be the most painful part of the entire thing. So, but how about we could do the following? We just mitigate on in the expectation value. So this also, of course, only applies to expectation value, but you mitigate the effect of having noisy T-gates in an actual error-corrected computation. Okay, and so what is the idea here? So imagine you could prepare some noisy version that is not very good, but a noisy version of a, well, it has to be pretty good, but a noisy version of a magic state. And then this noisy version of a magic state may lead to a noisy T-gate. And then the effect of that noisy T-gate, you might be able to fix using the quasi-probability method that we talked about beforehand. Okay, so there's a couple of technical things. So the first thing you have to actually do and worry about is, okay, in this setting, now you're sort of acting on logical qubits with your error mitigation protocol, only on single logical qubits. So it's a single logical qubit protocol, because you assume, say, yeah, okay, C naught is maybe given to you. And what you have to do is you have to do a couple of things to make things nice for you to work there. So how would you estimate what the actual noise rate is in practice? Can you shape noise in a way that it becomes nice? And how bad do things actually scale, and can you still gain a benefit? Okay, and so there's one way you can there's a neat way I'll talk about how you can twirl noise as an adoption of this of standard randomized compiling methods. Then you have to wonder, how bad does it get in terms of the hardware noise, and that strongly depends on the code that you're using. Okay, so let's start out with the assumption. So your goal is you want to prepare a magic state, but you end up with some noisy version of the magic state. What you can do is, as I said before, is you can apply logical twirling. So what's important is that you're actually dealing with a T-gate here, because you only want to twirl the stuff. You can only twirl gates that are in the third level of the hierarchy, of the Clifford hierarchy. And so if you now want to do Clifford, if you have available H, S, and the Pauli group essentially to do the twirling, you can do that. But the nice thing is that everything basically reduces down to only depending on one noise parameter in your T-gate, no matter what your actual physical noise is that is underlying them. Okay, and so what you can do then is basically you can define that one noise parameter in terms of the fidelity or infidelity between that noisy initial state and the resulting and the ideal magic state. Okay, so since it's only one noisy parameter, there's actually a very, very neat way of learning that noise. What you can do is you can basically start exponentially raising said gate, T-gate, to learn that the noisy T-gate to a higher power. And what you really see is that you have an exponential decay that only depends on that one noise parameter. Okay. Okay. Once you've learned that noise parameter, you can actually look for a quasi probability decomposition of your gate after you've applied the twirl, and you realize it's actually a pretty nice one. It's basically either only applying the noisy gate with a certain probability, or basically flipping in the Z base, applying a Pauli Z flip of the same noisy gate. And so that linear combination basically gives rise to an ideal T-gate. It depends on only one parameter. Now the challenging question is here, okay, now we've done a lot of things, right? I mean, I have skipped over all the details, and you want to know, you want to have an encoded magic state, right? And your worry is now, okay, you don't want to do distillation, or you want to do only limited distillation, so you can do that. But say, is there any hope that this is not this is not going to blow up with the code distance? So anything where you spend time with increasing the code distance is going to make it work. And so there's a very nice result by Ying Li, which basically shows the following: that it is possible to if you by a certain form of state injection and a certain protocol, to implement, if you have like two logical qubits, to implement one version of a noisy magic state, And interestingly, that noisy version of that magic state only depends essentially linearly, roughly, onto the errors that you have in the protocol. So you could imagine, okay, maybe that epsilon bar would grow with code distance, it would get worse with code distance, and so forth. But it turns out it doesn't. So it only depends sort of on your single qubit errors, epsilon 2 qubit errors, epsilon 2 single qubit errors, and say your initial errors. It uses some post-select and stop initial step, which is rather mild, but in principle, what you know is, oh, you can actually generate an effective noise rate that is comparable to the actual physical noise rate of your components. Okay, and let me transition to the next slide. Okay, so then that said, if you look at that and if you crunch some numbers, basically, is that actually worthwhile doing? Right. So I mean, you can ask yourself, okay, I'm now paying again an exponential cost in implementing T-gates, albeit a weekly exponential cost. How does that compare with other things? So, of course, your scaling is way better if you just use conventional quantum error correction. But let's say we're in the setting that doing magic state distillation, many other things, or actually implementing that in a device becomes really, really painful. So we sort of move away. We're not there yet. And then you could ask, well, on the other end of the spectrum, you know that there's, for instance, David Gossett and Sergey Bravi, they've come up a while ago with a simulator of quantum circuits that also scales sort of relatively weakly exponential in the number of T-gates that you would like to apply, and compare that how far you get there. So if you look at very ambitious, not unrealistic noise rates, you could potentially say the estimate. So you have like assume you have depolarizing noise. You do so we modeled it numerically with measurement, readout errors, all these things. But you assume those depolarizing noise rates, say around 10 to the minus 3, 10 to the 10 to the minus 4, so 5 nines. So that's 4 nines. Yes, that's challenging, but we're assuming we're already on the way towards fault tolerance. You can see that realistically, using Sergey and David's method, you could probably implement about 50 T-gates. Whereas using that sort of gets you in the order of 10 to the 3, 10 to the 4 potential T-gates with a sampling overhead that is like, 1,000, 10,000 potentially. Okay, so it might be worthwhile doing in the interim from when the first devices come out that actually have logical qubits and allow you to do Clifford gates. Maybe one more thing I want to point out is that in that process, we've been also thinking about other ways of actually generating a noisy magic state. And one way we found to do that is basically one way you can do this is basically by code deformation of a single qubit. So the nice thing is, yes, you don't have 2 logical qubits, so you save on that. However, you only can do it with a single logical qubit. However, the constant, which is numerically including measurement errors, is sort of 22 as opposed to order 1 to 2 as it was in the other protocol. So there's a small trade-off. I think I may have gone pretty fast, but I guess there's probably time for questions. So with that, I'd like to conclude and thank you all.
Thank you very much, Kristan. This was a great talk. So let me check the slide. I think there is a question of Tom. So maybe Tom will ask personally, right?
Yeah, hi, Kristan. Thanks for the talk. That was really good, really interesting new work. I guess I was wondering, is there anything special about using the quasi-probability method here, or could the same ideas be extended to any other error mitigation technique?
So for the noisy T-gate,
yeah.
So in principle, I'm not seeing a reason why you only have to use the quasi-probability method here. We used the quasi-probability method because it was all very controllable and nice, and we can understand what's actually what's going on in that sense, and that's why we centered and did that in the end, because there are certain operations which come kind of natural and nice. So for instance, if you think about stretching, that might be a bit painful, but maybe possible and so forth, or there could be other ways, yes. But a priori, there's of course, I don't know. I mean, people can come up with other things that might work better in certain settings, but we sort of focused on that for now.
Yeah, sure. I don't think that diminishes the work. It makes it more practical.
Do we have some other questions? We still have some time. No questions here.
I guess maybe I can ask another one.
Sure.
Yeah. So I mean, you've said you assume that you have fault-tolerant logical operations here on
Clifford.
fault-tolerant Clifford operations here. Is your assumption that these effectively have zero error?
No. So I didn't talk about that a bit, but part of that goes actually, yes, you have, of course, you have with code distance exponential error suppression, but then if you bound, there's actually some subtlety in how the actual error propagates for the error mitigation, because the map, actually the inverse map is not a physical map, so you have to be a bit careful in how you propagate this. But this is something, yes, we analyze so in the paper. So what you would do in that case is basically that error basically grows like, because you have a growth in code distance, and it does grow slightly weakly exponential in the code distance as well. But there's a very simple trade-off they can make, that it grows much weaker than your original error that you have, right?
And so I guess, I mean, you're like, do you then have to worry about, because when people compile fault-tolerant algorithms, they don't really worry about routing, because we just kind of assume that, you know, routing will be so much less than the cost of input of generating a single T-gate. But have you considered that here as well?
Oh, that's an interesting question. We have not. So we have, so to be clear, we haven't. So one thing we haven't done in general is basically, you can of course now in those numbers, it just bears that, okay, you just have this many T-gates in the circuit. Of course, what you can worry about are many things, such as basically, well, is in the same sense, what is it? How do you want to optimize your circuit now? Do you still want to optimize it for T-gates? Yes, you probably do. What becomes painful? What code do you want to use? What distance do you want to use, and so forth? Which algorithms are sort of very nice, where you're in a scenario where you have like a lot of Cliffords and quite a few T-gates, but maybe not too many, and so forth. These are all considerations that we deliberately didn't put into that paper, because there's a myriad of different answers that you could give.
Mm-hmm.
Right?
Yeah, thanks.
Thanks.
Cool. Okay, no other questions? Maybe I can ask one, very naive one, from the perspective of a quantum chemist, okay, waiting for a practical application. So if you take everything together, I mean the number of qubits, the length of the circuit which you can afford, error mitigation and things like that, what is the progress over the last few years? Do we see, can you say that, because you work for IBM, right? So can you see this is like a polynomial or exponential? Is there something like a Moore's law for NISQ devices, or this is?
Okay, so something that I frequently showed is basic, which I didn't hear, is basically if you like starting in the 90s until now. So say there's many errors, and there's many things you have to consider and so forth. But let's look at the simplest figure of merit. You just coherence time, right? And what you can see is that, yes, if you now plug that on a log scale, ignoring all the technical advances, you really see a wonderful line on a log scale. So yes, you do have, in coherence times, you have very neat exponential progress. And I think, like, for select single qubit devices, even a few years back, people were actually able to produce half a millisecond coherence times. I think we had a blog post about that. So yes, there is really genuine progress, and so forth. But taking everything together, I don't think I would like to say anything.
Okay.
Right? I mean, there is progress. There's a lot of progress, but what I would wait for is to actually see whether this stuff holds up in an experiment before I run out and conjecture stuff and in 4 years everything is going to be different. No, I just can't. Right?
Sure. I see. Okay, thank you very much.